What's up? I'm Vin, and today I want to go through an AP Calculus ABBC Unit 6 practice test. I'll leave a link to a copy of this test in the description below, so let's get started. Now, just know questions 1 through 15 are going to be topics that are on both the AB and BC test, whereas for questions 16 through 20, that's just BC stuff. And at no point are we going to be using a calculator. And first up here, we're just doing this antiderivative. And the first thing you would do here is just translate this expression to x times x to the 1/3 power. So we're just going to get rid of that cube root, and then we could tack on our dx. And then if we simplify the bottom, when you do x to the first times x to the 1/3, you add exponents, you're going to have x to the 4/3. And just know when you want to use power rule, your integral has to be in the form of x to a number power. So we're going to rewrite this as x to the negative 4/3. And now we tack on our dx here. And just know for this, we're just going to be adding 1 to the exponent. So we're going to have x to the power negative 4/3 plus 1. And a little mental trick here, when you're adding 1 to a fraction, what I'm doing in my head is I'm doing the numerator plus the denominator over the denominator. So if I do this, negative 4 plus 3 is negative 1 over 3, and then just divide by negative 1/3, which is the same thing as writing the reciprocal in front. So I would have 3 over negative 1 in front like this. We tack on our plus c. But of course, this I would simplify in my head. I'm just showing this for instructional purposes. 3 divided by negative 1 is negative 3. So you have negative 3x to the negative 1/3 plus c, and this is going to match up with choice B. Now, before we move on, something like choice C is a very dangerous bear trap. For something like this, a student is not going to simplify first, and they're just going to go ahead and power rule this at this step and say 1 over x to the 4/3 plus 1 would give you 7/3, and then they tack on their 3/7 with the plus c. But remember, you need to rewrite your integral in the form of x to a number power if you're going to use the power rule. So just be careful of this. Choice B is our answer. So question 2, we need to know the fundamental theorem of calculus here. And to evaluate this definite integral, we're just going to do the antiderivative first. And the antiderivative, if I'm doing this in my head, I'm going to have 3x to the power 3, and then I'm dividing by the new exponent, which is going to cancel this. So that's why this starts out as x to the 3rd minus, we would have x to the 2nd divided by 2, which I could write as 1/2 x squared. And now I'm evaluating this from 1 to 2. So to complete the fundamental theorem, we're going to plug in the top number, bottom number, and subtract. So we're going to have 2 to the 3rd minus 1/2 2 squared. And then in the second set of parentheses, we're going to plug in 1. And we just have to be careful subtracting here. So this is going to give us, we're going to have 8 minus, to order of operations, 2 squared is 4, and half of 4 is 2. So we have 8 minus 2 minus, and I'm going to have 1 minus 1/2 is 1/2. So now we just work this out. This is going to give us 6 minus 1/2, and this we could rewrite as 12 over 2 minus 1 over 2. So that's why this one's going to work out to just 11 over 2 after we do 12 minus 1. This matches choice C. So question 3, we have another definite integral, but this time we're going to do a u substitution. So in this case, we're going to let u equal the bottom piece, which is going to be e to the x plus x. Now, I know that this is going to be our selection of u because if you take the derivative of this expression in your head, this derivative is not too bad to do in your head. It's going to be e to the x plus 1. And then we just tack on our dx here. So du is equal to this. And notice that we have e to the x plus 1 dx on top. So that's how I know I'm going to go with this selection of u. But one skill that's very useful to show up with is when you do a u substitution and it's a definite integral, what you could do is you could plug in the old limits here. These are x equals limits. You could plug in the old x equals limits into your definition of u. So then my new upper limit would be e to the power, and we have x equals 3 plus x equals 3. And then on bottom here, I would plug in x equals 0, and I would have e to the 0 plus 0, which would just simplify to 1. So now what I could do is I could rewrite our integral. And we're going to have the integral of e to the x plus 1 dx. That's just du on top. And on bottom, this expression is equal to u. And then our new limits of integration are going to be 1. So we have 1, and we have e to the 3rd plus 3 like this. So now we just antiderive this. This is natural log absolute value of u. And we're going from 1 to e to the 3rd plus 3. And the benefit of doing it this way is that we don't have to switch everything back in terms of x. We could just proceed with these new limits. And now we're going to have natural log absolute value of e to the 3rd plus 3. And then we're going to subtract the result of plugging in 1. And just know here, natural log of 1 is equal to 0. So this piece cancels out. And this is a positive expression here. So we could just write natural log of e to the 3rd plus 3. And this is going to match up with choice D. So question 4, we have a left, right, and trapezoid sum is used to approximate this definite integral. So first I would just draw out, what is that definite integral model? It models the area under the curve of f of x equals x squared or y equals x squared, doesn't matter, but going from 0 to 3. So if we're talking about the exact area here, I'll just underline this in pink. That's referring to this space here under the curve. So let's just make this as neat as possible. So this models, once again, the exact area under the curve, which represents that definite integral over here from 0 to 3. But now let's say for all these approximations, I just do two subdivisions here. So let's say I do the right Riemann sum in red here, and I'm going to choose these 2 points here. So this is at about the 1.5 mark. And if I'm choosing between 0 and 1.5, my rectangle is going to be at a height determined by the function at 1.5. So this would be my right Riemann sum like this. And you could see here that the right Riemann sum is going over the actual area. So the actual area is in pink, but the right is going over. So that means the definite integral has to be less than the right Riemann sum. So just looking at this, you see how in choice B, the right Riemann sum is less than the actual area. So this choice is out, and this choice is out for the same reason here. But now we have to look at the others. So for the left Riemann sum, I'm choosing between 0 and 1.5. I'm going to use the function value determined by 0. And then between 1.5 and 3, my rectangle is going to go to this height like this. So the left is definitely going to be less than the right, but that shows up in both of the remaining choices. So now the $1,000,000 question here is, what is going to be a bigger value? Is the trapezoid sum going to be bigger than the actual area, or is the actual area going to be bigger than the trapezoid sum? And the trapezoid sum you would get by connecting these 2 points like this to form a trapezoid. So you see here, if I look at our trapezoid, this is going to be the result of connecting these 2 points. And because x squared is concave up, any one of these trapezoids that we make, even though technically this one here is a triangle, is going to go over the curve. So the trapezoid sum is going to be an approximation that's over the actual area. So this one here is going to match up with choice A. So for question 5, we're talking about the area from 1 to 4. So I'm just going to draw this out here. The area from 1 to 4 of g of x is going to be equal to 6. So this is not necessarily what g of x looks like, but this entire area is equal to 6. And then if we look here from 3 to 4, so this is not drawn to scale, but from 3 to 4, the area is going to be 4 square units. So we want to know, what is the mystery area here from 1 to 3? Now this, you could just probably think about that it would have to be 2, because 2 plus 4 would give you 6, and that would be choice B. But if you really wanted to write out a technical response, just know that the entire area from 1 to 4 of g of x is equal to, we could break this into two integrals going from 1 to 3 of g of x, and then we could add the integral from 3 to 4 of g of x. So this is just a nice property here for definite integrals. So then if we made the substitution, you see from 1 to 4 it worked out to 6, and then from 1 to 3 is what we're actually looking for. And then the last piece here, from 3 to 4, the actual area was 4 square units. So here we would just have to subtract 4 on both sides. And notice when we isolate the definite integral, it does work out to 2. So choice B is our answer. So question 6, we have a graph of f prime question, and here's the graph of f prime. We're told that f of 0 is equal to 2. What is the value of f of 6? Now you could just know this formula here, that we could say that f of 6 is equal to f of 0 plus we have the integral from 0 to 6 of f prime of x dx like this. But this might be a little bit tricky to memorize. So for students that can't memorize, like let's say you're not going to remember this, but you do know the fundamental theorem of calculus. Well, that you could just write out then directly. The integral from 0 to 6 of f prime of x dx is equal to the antiderivative of f prime is f, and then I evaluate it. So this is by the fundamental theorem. I evaluate it at 6 and 0, and I subtract. So I have f of 6 minus f of 0. So just know that you're always going to be writing the initial condition here. Okay, so the initial condition is usually going to be your lower limit. Sometimes you'll make it your upper limit, but it's usually going to be your lower limit. So that's where you write your initial condition. And once you have this here, the rest is just using the graph. So if I wanted the area from 0 to 6, notice that these are both straight line segments. So I'm just going to find the area of all these shapes here. So this is a triangle, and the area of a triangle is 1/2 base times height. So that's the area of a triangle. So if I just do 2 times 3 is 6, and then I cut it in half, that's going to tell me this is 3 square units. And then if I find this area here, notice from 2 to 5 is a distance of 3, and the height of this triangle is going down 1, 2, 3 like this. So this is going to go 3 times 3 is 9, and then half of that is going to be 4.5. But one thing to be careful of is that this is signed area. So we have to treat this, as negative area. Okay, even though area as a geometry concept is not negative, when you're just evaluating definite integrals, you treat it as signed area, so this comes up negative. And then this last triangle here, in this space from 5 to 6, we could find the area of this piece. This is going over 1 and up 3, and if we do 1 times 3 is 3, half of that is 1.5. So now we just work everything out here. So what we have is the integral from 0 to 6. I would have 3 minus 4.5. So I have 3 minus 4.5 plus 4.5 is equal to f of 6 minus f of 0 is equal to 2. But notice here that I have 3 plus 1.5 is 4.5, and 4.5 minus itself is 0. So this is going to give me 0 equals f of 6 minus 2, which tells us that f of 6 is equal to 2. Choice B is our answer. So question 7, this is a tricky integral, and choice A is a very dangerous bear trap. The problem with this answer choice here is that if you were to let u equal x squared minus 4x plus 5, du would just be equal to 2x minus 4 dx. But the problem is that we don't have a linear factor on top that matches this expression or a multiple of this expression so that anything would cancel out. So we're not going to be able to do a u substitution involving natural log. So then we could use the remaining answer choices here as a guide. So when I see tangent inverse, what I'm thinking of right away is if I could somehow turn my integral into something that looks like this, du over 1 plus u squared, then we'll be in business and be able to work this out. So my first instinct then, based on that, is to break off a 1 on bottom and write this as 1 plus, and I would have x squared minus 4x plus 4. Now notice what this just accomplished for us. This is something that's factorable here, that I could break this down now as dx over 1 plus, and that term factors to x minus 2 squared like this. So now we can do a u substitution. Although if we skip the u substitution here, we can get away with this and see that this is just going to work out to choice C. But let's say we want to show all the work. We have u equals x minus 2. So du would just be equal to 1 dx. And now we go ahead and make the u substitution. We're going to have the integral of du over, we have 1 plus u squared when we replace x minus 2 with u. And now this is going to work out to tangent inverse of u plus c. But when we substitute back in for u, that's going to be tangent inverse of x minus 2 plus c. Now the reason why we could skip u substitution is because the derivative of our u term is just equal to 1 dx. So anytime that happens, that means you could skip the u sub step. But otherwise, either way, we're going to get choice C. So question 8, we have a definite integral, and we can do this with u substitution, but there's a nice shortcut here. Anytime your u term is linear, so this works when you have a linear u term. If I have something in the form of u equals mx plus b, then what you could do is you antiderive. So I'm just going to abbreviate. You antiderive, and then you divide by, so more abbreviation here, you divide by the derivative of your u term, which is m. So in this case here, if I want to do this via shortcut, I'm just going to think of this as, instead of square root, we're going to have to the power of 1/2. So I start by doing the power rule. I'm going to have 10 minus x to the 1/2 plus 1 is 3/2. And the reciprocal of 3 over 2 is 2 over 3. That goes in front, but now this is the shortcut step. We're going to divide by m. So our m value here is going to be -1 because that's the derivative of 10 minus x. And if I divide by -1, that just throws a negative in front like this. And now I tack on my limits of integration, which are going from 1 to 6. So now we just simplify this. I like to write my constant in front. So I have -2/3 in front. And now I'm going to have here, I have 10 minus 6 to the 3/2 power minus, and when we plug in 1, we're going to have 10 minus 1 to the 3/2 power like this. So now we just have to be able to evaluate these expressions, no calculator. Just know this is the power over the root. So when I simplify this in my head, the first thing I'm simplifying here is I'm doing the square root of 4, and that's being raised to the 3rd power. So I have -2/3, and if I do the square root of 4 is 2 to the 3rd power is 8, and now I have minus. If I do this next part, I have the square root of 9 to the 3rd. So I have the square root of 9 raised to the 3rd, and that's going to give me a 27 here. So now we just have to subtract this, and this is going to be -2/3. 8 minus 27 is going to give us -19. And when I do -19 times -2, that's going to give us 38 over 3, and this is going to simplify to choice A. So question 9, we have another u sub, except this time u is equal to cosine x. And when we calculate du, we're going to get negative sine x dx. And now what we could do here is we could solve for dx, so we could divide both sides by minus sine x. And from this step, what we have now is we have dx is equal to du over negative sine x. And then what we could do is we could find new limits of integration. So u equals. Our old limits are in terms of x. So just plug them into our definition of u here. And I would have cosine of pi is my upper limit, and cosine of pi is -1. And then as my lower limit, I would have cosine of 0 when I plug in, which is equal to 1. So now I could just go ahead and transform this integral. We're going to now have the integral going from 1 to -1. And make sure that you write this in the order as it appears. So notice that this was our upper limit and our lower limit. So don't swap these and hope no one notices, because that sign change can affect your answer. And we're going from 1 to -1. And then instead of cosine squared, that's our u term squared. So I have u squared, and then I have sine x, and then dx is equal to du over negative sine x. So notice that the sine x is canceled. And if you do your u sub correctly, you should have all new variables here, none of the old variables. So now I'm going to take this negative over here, and I'm going to bring it outside the integral. So I have the integral with a minus here going from 1 to -1. And we're left with u squared du. But this is not looking good. So what I would do is I would flip the limits of integration, and that's going to change this minus to a plus. So this is a much nicer looking integral like this. And that brings us here. Now, if you really want to be fancy, you could use the fact that u squared. So u squared as a function is even. So if I'm finding the area from -1 to 1, just know that that's symmetric. So what I could do is I could rewrite this as 2 times the integral from 0 to 1 of u squared du like this. So this is just reviewing all the concepts of integration we can make use of. So we have 2 times, and we have u to the third over 3, and we're going from 0 to 1. So now we just plug in. We have 2/3 times, so I leave the constant out, and I have 1 to the third minus 0 to the third, which is going to be 2/3 times 1, which is just 2/3. Choice C is our answer. So now we're going to use the table of values of twice differentiable function f of x to answer questions 10 through 12. And for question 10 here, we're computing a left-hand Riemann sum for this definite integral using 4 subintervals. So for a question like this, it doesn't hurt to draw this out, especially if you forget how to do this the shorthand way. So at x equals 1, we have a y value of 2. And then at x equals 1.5, we're going up to 6. Now, I'm not drawing this to scale. This is just to get the idea across. When I go out to 2.5, so I go over here, we're going up to 7. And then when I go out to 3, we're going up to 10. And then one more, we're going out to 4, and the y value is going up to 12. So with this, if I'm doing a left Riemann sum with 4 subintervals, between 1 and 1.5, I have to make a decision, but I'm choosing the point on the left to make my rectangle. So there's my first rectangle. And now this rectangle is going to be decided using 1.5, and I draw my horizontal line going this distance from 1.5 to 2.5. Now between these two, I'm choosing 2.5 because it's on the left. And then for the last subinterval between 3 and 4, I'm choosing the x value here at 3 because that's to the left of 4. And there's my 4th rectangle. So now it's just a matter of finding the area of these 4 rectangles and adding them. So notice here that I'm focusing between 1 and 1.5. The y value we used is 2. But notice this distance here is 0.5. So I have 0.5 times the height of 2. And then I'm going to be adding from 1.5 to 2.5 is a distance of 1. And the height that we used was 6. So this is, once again, if you forget formulas, this is a real visual way of doing this, and it's pretty nice. So we have 0.5 next is the distance from 2.5 to 3, and we're going up a height of 7. And then last, our delta x from 3 to 4 is 1, and we're going up a height of 10. So now it's just a matter of doing the arithmetic, being careful. So half of 2 is 1, plus we have 1 times 6 is 6, and then we have half of 7 is 3.5, and then 1 times 10 is 10. So now we just add this up carefully. So we have 7 plus 10 is 17 plus 3.5 is going to be equal to 20.5. And this is going to match up with choice B. Now, a fast way to go through this for questions like this, when you have 4 subintervals, you could just pick the 4 y values to the left like this. Notice 2, 6, 7, and 10 show up, and then you calculate the 4 delta x's. So 1 to 1.5 is going to give you 0.5. From 1.5 to 2.5 is 1. So you could just go that way very, very quickly. But once again, if you're going to forget that idea, drawing it out is a way to really feel safe that you're doing this right. So question 11 is so easy that it's difficult. So for something like this, all you need to do is take the antiderivative of f prime. We're using the Fundamental Theorem of Calculus, and the antiderivative is f of x. And then we're evaluating this from 1 to 4. So then you just plug in. You got f of 4 minus f of 1. And if you look at the table, f of 4 is equal to 12. So this is 12 minus f of 1 is equal to 2. And 12 minus 2 is 10, so this matches up with choice A. So for question 12, we have g of x is equal to this area function here. We want to know the value of g prime of 1.5. So for this one, I wrote out this very long formula here, which is called Leibniz's rule. And for this one here, anytime you have an area function like this and you want to take the derivative, the shortcut here is just to plug in the upper limit function into the integrand here. So I'd have f of 2x, but then this is the sneaky part. We also have to multiply by the derivative of the upper limit, and the derivative of 2x is 2. And then when I plug in the lower limit, I'm going to have f of 0, but then I'm multiplying by the derivative of the lower limit is 0. So this last piece wipes out. So this tells us that g prime of x is equal to 2 times f of 2x like this. So now g prime of 1.5, I would just substitute in 1.5. I have 2 times f of 2 times 1.5 is equal to 3. And then I just have to go looking in the table. F of 3 is equal to 10. So I have 2 times 10, which is equal to 20, and this matches up with choice B. So question 13, we have f of x is continuous, f of x is less than or equal to 8, and we want to know what is the largest possible value of this definite integral here. Now this question is very easy to overthink, but if we want to make the definite integral, the area under the curve, as large as possible, then we want to make f of x as large as possible. So we could just fix f of x to be the line y equals 8. So when we find the area from 2 to 4, then we're just going to be finding the area of this rectangle here. And notice that this rectangle is a 2 by 8. So it's going across 2 and it's going up 8. So we just do 2 times 8, and the area on the inside is going to be 16 square units. So choice B is our answer. So question 14, we have f of x is a piecewise function, and we're computing this definite integral. So it really helps if you're able to draw these out, because anti-deriving each piece is going to be a nightmare. So here, if I look at x squared plus y squared equals r squared, this is a circle centered at the origin with radius r. But then if I solve for y, this is going to give me y squared equals r squared minus x squared. I take the square root of both sides, and now I have y equals plus or minus the square root of r squared minus x squared. So what this just accomplished here is we have an equation for the top part of this circle, so this semicircle going above, and then the minus square root would give us the bottom part of this circle here, so the bottom semicircle. So looking at our f of x, one thing that jumps out at me right away is that our r value is equal to 2, and since we have a positive invisible 1 in front of our square root, this is going to be a semicircle that's opening upwards. So the center is at 0, 0, and the radius is 2. It's going to look something like this. So we're going left to -2, to the right to +2, and we're going up to 2 here. But then the graph turns into the absolute value of x minus 3. So if I look over here at x equals 3, I'll extend this out a bit. What we have here is, if I look at the beginning at x equals 2, 2 minus 3 is -1. The absolute value of -1 is +1. So this absolute value is going to start here. It's going to go down to 3, 0, and then it's going to make its turn. And it's stopping over at x equals 5. And if I do 5 minus 3 is 2, that tells me the height it's going to leave off at is going to be over here at y equals 2, at that height. So now when you think about what are we looking for, we want to find the area under the curve from -2 to 5. So we're going to be finding the area of this piece here, and then the circle stops over here at x equals 2, and then it becomes, we have this triangle, so we have 1, and then we have this piece over here. So for this one, we could just go ahead and do this, and notice here what we have. We have a semicircle with radius 2. So this is going to be pi times 2 squared, but we're cutting it in half because it's a semicircle. And that's just going to be equal to 2 pi. So I could just label this over here. This piece is going to be 2 pi square units. And then over here we have a triangle, and remember this is going up to a height of 1. So what we have is, this is a distance of 1, the height of this triangle is 1. 1 times 1 is 1, and if we take half of that, this area is a half. And now this one is going across 2, because it's going from 3 to 5, and it's going up 2. And if you do 2 times 2, that's 4, but since it's a triangle, the area of a triangle is 1/2 base times height. So half of 4 is 2. So now just add everything together. So altogether, we have the area of the semicircle is 2 pi, plus we have 1/2 is the area of the first triangle, plus 2, and this is going to give us 2 pi plus 2.5, and 2.5, another way of saying this is 5 over 2. So 2 pi plus 5 over 2 matches up with choice B. So question 15, we have f and g of x are twice differentiable for all values x. F of x is less than or equal to g of x. Which of the following must be true? So for this here, I would go through each Roman numeral one at a time. So let's say the first one. Something like f prime, you should know, is the slope of f of x. So I'm going to try to draw this in such a way that f of x is definitely less than or equal to g of x, but this condition is not satisfied here. So let's say I draw something kind of like this. So here's f of x, and g of x I'm going to draw kind of like this. So what we have here is if I look at this location, notice right now at this location here that f has a positive slope and g of x is decreasing slightly here, has a negative slope. So here's a situation where f prime at, let's say, c, I have f prime of c is positive, but g prime of c is negative. So you see how that contradicts Roman numeral 1, because here we have it, that at this location that wouldn't be true. Because if f prime is positive at c and g prime is negative, then f prime is not going to be less than or equal to g prime. So that one is out. And now for the second one here, Roman numeral 2, just know that f double tells you the concavity of f, which tells you the shape. So if f double is positive, this is going to mean the graph of f is smiling at us. Whereas when f double is negative, that means the graph of f is frowning at us. So looking at this here, the way I drew this piece concave down and this one concave up, but I could just as easily draw this a different way. I could draw my graph where g is frowning for this part. So maybe it does make a turn and become concave up, but it's like temporarily concave down. And then my graph of f underneath is concave up for this portion, but then switches to concave down. So here's my graph of f, and here's my graph of g. The condition is satisfied here. F of x is less than or equal to g of x, but notice here at, let's say I call this at point C, that I have f double prime of c is clearly greater than 0 because this portion of the graph is smiling. Whereas over here, if I look over here, we have g double prime of c is less than 0 because that portion of the graph, if we highlight it, is frowning at us. So this condition here is not necessarily true, but this one must be true. The reason why this one must be true is because if f of x is less than or equal to g of x, that means that this graph is at the very least equal to or always above f of x. And if it's always above, this is the area under the curve. So if you just think about it very carefully, if g of x is always above f of x, then it's going to have a higher area because the y values are going to be higher as we find the area from, let's say, 0 to 2. So let's say if I'm looking at this portion here, that's the area under g, and this one is the area under f. You can see that this area is definitely higher. So it's just going to be 3 only. Choice B is our answer. So we move on to the BC only questions, and first up we have an improper integral, and I'll pretend like notation matters. Even though it's multiple choice, they don't care about your notation there, just if you bubble correctly. So I'm going to rewrite this as the limit as b goes to infinity of the integral from 1 to b, and I'm going to rewrite the inside as x to the negative third dx. So for this one, I would just do the FTC here, the Fundamental Theorem of Calculus, and I would have x to the negative 3 plus 1 is negative 2. I divide by negative 2, and we're evaluating this from 1 to b. And now one thing I like to do for questions like this is I'm going to plug in, but that 1 over negative 2, I'm going to leave out on the side like this. And I could write it as 1 over negative 2 or negative 1 over 2. It's the same thing. And now we're going to have b to the negative second minus, we plug in for x, we have 1 to the negative second. And now this is going to simplify. We have the limit as b goes to infinity. We have negative half. And now we've got 1 over b squared minus 1 to any power is just 1. So now this simplifies to negative 1/2 times, and as b goes to infinity, 1 over infinity squared goes to 0. And I have minus 1, and negative half times negative 1 is going to give us positive half. Choice B is our answer. So question 17, we got to know integration by parts. We want to know what is this definite integral here. And for integration by parts, you should be looking for something in the form of the integral of u dv is equal to, we would have u times v minus the integral of v du. So for this question here, what you want to do is you want to define your u term and your dv term. But in this case here, u should equal x. The reason being that if we were to let u equal g prime, then we would take the derivative and get g double prime, and we don't know anything about u double prime here. So now that means we're going to define dv to be equal to the rest of the integral, which is g prime of x dx. So now we're going to calculate du, which is going to be equal to 1 dx, and then v, the antiderivative of g prime, is g of x. And we don't have to worry about plus c here because we're doing a definite integral. And even if it were an indefinite integral, we would tack that on at the very, very end. So now we go ahead and we apply integration by parts here. So now for this one here, what is this equal to? Well, we're going to do u times v. So we're going to have x times g of x. And just know this is a definite integral, so we're evaluating this from 1 to 3. Minus, we have the integral of v times du, which is g of x dx, but this is a definite integral going from 1 to 3. So now notice what we have here. They told us that the integral from 1 to 3 is equal to 9. So ultimately, we're just going to have a minus 9 at the end. But now we're going to plug in 3. We have 3 times g of 3 minus, and I'll just put this part in parentheses here. We have minus x equals 1 times g of 1. And now the rest is using the given information here. So we have 3 times g of 3 is equal to 6. Minus 1 times g of 1 is 2. Minus 9. And this is going to give us 18 minus 2 minus 9. And 18 minus 11 is equal to 7. This matches up with choice C. So question 18, we're doing another integral, and we're doing integration by parts. And liate is a helpful mnemonic, especially if you have something in this form here. If we had something like, let's say, x times e to the x dx. Our x term is something algebraic, and our e to the x term is something exponential. And notice that algebraic shows up before exponential. So by default here, in a case like this, our u term would be equal to x. But in the example we're looking at over here, notice we just have tangent inverse. So that by default is going to be our u term. Because if we set it equal to dv, then we would be finding the antiderivative of tangent inverse, which is our objective anyway. So that wouldn't be our dv term. So in this case, dv is just going to be the leftovers, which is going to be dx like this. And now we're going to calculate du, which is 1 over 1 plus x squared, and we tack on dx. And then our v term, the antiderivative of 1, is going to be x. So we have u times dv, and now we could apply the integration by parts formula. This is going to be equal to, we have the product of u times v, which is x tangent inverse x, minus the integral of, we have x times this expression here, which will give us x over 1 plus x squared dx. And now we're going to have to do another substitution, but this time I'm going to call it a p substitution. I'm going to say p equals the bottom here, 1 plus x squared. And then the top, I'm going to say is dp. Well, first let's find dp. dp is equal to 2x dx. So when I look at this top expression here, I have an x dx. I could isolate x dx if I multiply both sides by a half. So I'd have 1/2 dp is equal to x dx. So this allows us to now say in the next line that this is equal to x tangent inverse x minus, and then x dx on top, I'm going to put a 1/2 in front, and then I have in the integral dp over the bottom, we're just going to call p. So now we're ready to do the antiderivative step here. And we're going to rewrite this. This is going to be x tangent inverse x minus 1/2 natural log absolute value of p. And then I throw on my plus c here. And remember, p was equal to 1 plus x squared. And since 1 plus x squared is always positive, we could just throw the parentheses on like this. It could drop the absolute value. And now we scan the answer choices and you're like, oh no, my answer is not there. And it's definitely going to be one of the last two. But notice they sent the 1/2 back into the log as an exponent. And if we do that, when we raise something to the 1/2 power, that's the same thing as having a square root. So we could say this is x tangent inverse x minus natural log of, we have this expression here, now to the 1/2 power. And then I throw on my plus c. But once again, what I could do is I could get rid of this 1/2 exponent and I could convert it to a radical and say square root like this. And now when we scan the answer choices here, this is going to match up with choice D. So question 19, we've got partial fraction decomposition. And for these questions, it is 90% algebra. The calculus is the easy step. The algebra is definitely the hard part. And what you're going to do for a question like this is first you're going to factor. And the giveaway for this question is that all the answer choices have the factors. We have 2x plus 1 times x minus 2. So once you get this to the factored step, the actual decomposition here is to say that this expression in factored form, so we have this is equal to, and I'm going to set this equal to the sum of two fractions. So this I could say is equal to, and let's just make this a little bit neater. We have a over 2x plus 1 plus, I'm going to leave a space here, we have b over x minus 2. Now, if you're really comfortable with the algebra, at this step, I go right to this equation. I say that 1 is equal to a times, we have the other factor is x minus 2, plus b times, we would have the other factor is 2x plus 1. So this, if I want to get to this equation here, I'm just multiplying this first fraction on the right side by x minus 2 over x minus 2, and I'm multiplying the second fraction here by 2x plus 1 over 2x plus 1. And when we do this, see how all the denominators match. So in a sense, they just all cancel out like this. and it gives us this equation we have in green. And now once we have that equation in green, we'll be able to solve for the values of a and b. Now you can use a system of equations here, but my preferred method is to plug in values of x that make the factors go to 0. So if I plug in x equals 2, I get 1 equals a times 2 minus 2 is 0, plus b times, I have 2 times 2 plus 1 is 5. And this is going to cancel out, and this tells us that 1 is equal to 5b, and that b is equal to 1 over 5. So this gives us the value of b. But now what we're going to do is solve for the value of a. And to do that, we're going to plug in the other factor here. Well, the root from the other factor. If you were to set this factor equal to 0, x equals negative half would make this equal 0. So the next test value I'm plugging in is x equals negative half. And I'm going to have 1 equals a times, and if I do negative half minus 2, negative half minus 2 is negative 2.5, which is the same thing as negative 5 over 2. So I'd have a times negative 5 over 2 plus b times, if we plug in x equals negative half, we're going to get 0 here. So this cancels out, and now this is going to give us the resulting equation. We have 1 equals, and we have negative 5 over 2 times a. So then if we want to just solve for a, we just multiply both sides by the reciprocal, and this tells us here that a is equal to, we're going to have negative 2/5. So now that we have our a and b values, this is going to tell us how to do the algebra to split up the original integral. So now we could rewrite this integral here as the integral of, and notice that a was attached to 2x plus 1, and b was attached to x minus 2. So at this step is where you could make your substitution for b and where you can make your substitution for a. But now what I'm going to do is we have 1/5, so I have 1 over 5, and then that was for our b term here, and I'm going to have dx over x minus 2. And then notice that the a term was negative, so I'm just going to write minus. The 2 over 5 I'm going to write in front like this. I'm going to factor it in front of the integral, and I have dx over 2x plus 1. Now, one very annoying detail here, I mentioned this a little bit before. If I have something in the form of dx over mx plus b, I could do a u substitution, but when my derivative of my u term is linear, like if I have a linear u term here, then the derivative of my u term, I'm just going to divide by that and go quickly. So this would actually work out to something like 1 over m natural log absolute value mx plus b, and then I would tack on my plus c at the end. So I'm going to use that shortcut because if you're not careful here, this is a very annoying bear trap to step in at the end if you forget to divide by the derivative of 2x plus 1. So for this first part here, we have 1/5 natural log absolute value x minus 2 minus 2/5, and I'm going to leave a space. We have natural log absolute value 2x plus 1. I throw on the plus c, but the derivative of 2x plus 1 is 2. And if I divide by 2, that's the same thing as multiplying by a half. So my 2 over 2 cancels. And now I have these two log expressions here. They have the same coefficient of 1/5. So now I could write this as 1/5. And then we have on the inside, I'm going to put parentheses. We have natural log absolute value x minus 2 minus natural log absolute value 2x plus 1. And then we could throw on our plus c at the end. But now to combine this, this is going to be equal to 1/5. Subtraction of logs, and let's just throw in that last piece of the absolute value. But subtraction of logs, you could combine by division. So I have absolute value x minus 2 over 2x plus 1. I close my absolute value, and then I throw in my plus c. And this looks like it is matching up with choice A. So question 20 is our last multiple choice question, and we're finding this improper integral here. We're integrating over an infinite discontinuity. We have a vertical asymptote at x equals 3. And if we sketch this function, this is 1 over x minus 3, which is a lot like 1 over x. It's just shifted to the right 3 units. So we're looking at this space here from 3 to 5. So if we go out 2 more like this, the $1 million question here is this area of this region under the curve. Is this going to be something finite, or is it going to diverge up to infinity like this? But notice the problem is the line x equals 3, or vertical asymptote. So if I look here, this limit x equals 3 is the problem. So if this were the free response, we would want to write this in terms of a limit. We would have the limit as b approaches 3, and be mindful, we're on the right side of the asymptote, so we're approaching 3 from the right side. So I would throw in a plus sign here. And now I have the integral from b up to 5 of 1 over x minus 3 dx. So now I just have to know my antiderivatives. So I've got the limit as b approaches 3 on the right side, and the antiderivative of this expression here, we're going to have natural log absolute value x minus 3, and I throw in my brackets here. I'm going from b to 5. And now I'm just using the fundamental theorem of calculus. So I'm going to plug in my upper lower limits and subtract, I'm going to have natural log, and if I plug in 5 here, I'm going to have 5 minus 3 is 2, and the absolute value of 2 is 2, minus I have natural log absolute value of b minus 3 like this. So now this is where the thought experiment comes in. It really helps to show up to the AP test knowing basic graphs. And one of the graphs that's considered basic for this test is the graph of natural log x. So here's the sketch of natural log x. And notice that at this point here, natural log of 1, we're at 0. But as we approach, so if I take the limit as x approaches 0 on the right side of ln x, be mindful that this graph is going down to minus infinity. So if I look here, notice I have ln to minus, and think about it as b approaches 3 on the right side. Like imagine you have something like 3.1. 3.1 minus 3 would give you 0.1. So you see this is a number that's slightly to the right of 0. So as we get really, really close to 3 on the right side, like let's say we did 3.0001 minus 3, see that we're basically following the path of this natural log function as we approach 0 on the right side. So we're heading down to minus infinity. And then notice here we have ln2 minus minus infinity. So this just goes off here to positive infinity. So the whole integral diverges. So let's move on to the part 2's no calculator. And we're just going to do one free response question here. So what we have here is we have a graph of f. It's a semicircle and 2 line segments. And what we have is the function g is an area function. G of x is the definite integral from 1 to x of f of t dt. And we need to find g of 1, g of negative 1, g of 3. So for a question like this, I highly recommend that you find the individual areas and then you combine everything at the end. So notice here, this semicircle, this is the center at negative 1, 0, and the radius is 2. So if we have a radius of 2, we could find the area is pi times 2 squared, but we're going to cut it in half because it's a semicircle. And 4 pi divided by 2 is 2 pi. So I'm just going to label that on the inside. But one thing to be careful of, this is area under the x-axis. So we have to treat it as negative signed area. And now looking at this triangle here, the area of a triangle is 1/2 base times height. So notice that this base going across is 2 units and we're going up 1 unit. So if I do 2 times 1 and then I divide that by 2, that tells me that I have 1 square unit of area over here. And now for this portion, this triangle over here, this is a 1 by 1. And if I do half of 1 times 1, this area on the inside is going to be 1/2 square units. So now we're ready to answer part A. Let's say first we want to find g of 1. Well, we just plug into this function here. This is the integral from 1 to 1 of f of t dt. And for this, anytime your lower and upper limits match, this integral is simply going to simplify to 0. So that's the first part here. And now for the second part, we want to find, I'll circle our answer. We want to find g of negative 1. And for g of negative 1, we're going to plug in negative 1 at the upper limit here. And we have f of t dt. So for this, I highly recommend that you flip the limits of integration when you're doing this, because it's much easier to read this from smallest to greatest. So we have minus the integral from negative 1 to 1 of f of t dt. And the actual meaning of the integral from this number to this number is the area under the curve. But notice where we're at here, that if we focus on this portion, if we start at negative 1 and we stop at positive 1, you see how we're just dealing with a quarter circle here. So what we're essentially dealing with is half of this area. And if the whole area is 2 pi on bottom, then this quarter circle is going to have an area of just pi. But once again, you have to be very, very, very careful here. This is area under the x-axis. So when we evaluate this, this is going to be, we're going to have minus pi. And minus pi simplifies to positive pi like this. So now for the last one here, we want to find what g of 3 is. And g of 3, we're just going to do the same thing as before. We're plugging into the function. So we're going from 1 to 3, and we have f of t dt. So now starting at 1 here, so we're starting at this location. If we want to go from 1 to 3, notice that it's just the area of this triangle, and that's just going to be 1 square unit. So here's our solution to part A. So now for part B, what we want to do is we want to answer the question, does g have a relative minimum, maximum, or neither at x equals 1? We need to justify our answer. So for this one, we could use the first derivative test. And what I would do here is find g prime of x. And g prime of x, by using the fundamental theorem of calculus, we're taking the derivative of an area function where the lower limit is a number and the upper limit is just x. So this we could just simply say is equal to f of x. So what I like to do for questions like this, notice g prime equals f. So I could also name this graph. This is also a graph of g prime. So this is going to come in handy when we answer the rest of this question. So now I'm just going to clear out some of what we had before. If we wipe this out here, notice that what I would do for a question like this is I would actually state, when is g prime of x equal to 0, g prime of x is equal to 0 when, and I could say here, x is equal to 1. Because notice we found g prime of x is equal to f of x, and we could clearly see here that the graph is equal to 0 at x equals 1. But now, one thing to pay attention to here is if you look at the behavior of the function before and after, notice that g prime, if I make a mini sign chart here, so a mini sign chart for g prime, that if I start my sign chart at -3 and I stop it at x equals 4, the two roots in between are going to be at x equals 1 and at x equals 3. So if I mark these off on my sign chart here, between -3 and +1, my derivative g prime is negative because it's under the x-axis. And then between 1 and 3, my derivative goes positive. And then from 3 to 4, my derivative goes negative. So if I look at the behavior of g, notice that this function, since g prime is negative, is decreasing. Then it's increasing, and then it starts to decrease again. So at x equals 1, if I go from decreasing to increasing, that's going to make a local minimum. So now we just have to write this all together. So moving on to part C here, I gave us some space, but for part C, we're going to use the extreme value theorem to find the absolute minimum and the absolute maximum. That's how we're going to justify our answer. So part of the justification here, remember what we said before. We said g prime of x is equal to f of x. And when you want to use the extreme value theorem, you should find the critical points, which is when, in this case, when g prime of x is equal to 0. And this is going to be true when x equals, so now we just find the roots. They occur at -3, at +1, and at +3 like this. So we have roots at -3, +1, +3. And then what we're going to do is make a table here for x, g of x like this. And we have to include the endpoints for the extreme value theorem. But we're also going to throw in the other critical points. So -3, we're not going to write twice, but we're going to include 1 and 3. Now remember from part A, we found g of 1. G of 1 was equal to 0, and we found g of 3 was equal to 1 like this. So this gets us started, but if I want to find the other values, you could just do this math in your head if you really understand accumulation. But what's going on here is if I go backwards from 1 to -3, I have to be careful. Technically this 2 pi is negative, but if I go backwards, the rules are reversed, and I could treat that as accumulating 2 pi if I'm going backwards. Because you could see here on our way from -3 to 0, this is a graph, once again, a graph of f, but it's also a graph of g prime. This tells us that g of x accumulates -2 pi. So I would lose 2 pi, sending me back to 0 like this. Otherwise, there's no shame in this. If I wanted to find g of -3 by hand, I just use my formula here. And this is the integral from 1 to -3 of f of t dt. And for this one, I'm just going to go ahead and flip the limits of integration and put a minus in front. So this would go now from -3 to 1. And from here, I'll leave the minus sign on the outside. And what is the area under the curve from -3 to 1? Since the 2 pi is under, I just have to throw a negative in front. And -2 pi is 2 pi. So that's why we have 2 pi here. But now to go from, let's say, x equals 3 to x equals 4, notice that we're losing 1/2 because the 1/2 area is under the x-axis. So if I do 1 minus a half, that's just going to give me a half like this. Otherwise, once again, I could find g of 4 using this formula, but it is going to work out to a half. So now we're looking for the absolute maximum and the absolute minimum. So this one here is clearly the biggest number in the list, 2 times pi. And then the smallest number in the list here, if we scan, is going to occur at x equals 1, where the y value is equal to 0. So for the last part of this question, part D, we need to find the x-coordinate of each point of inflection on the graph of g on this open interval from -3 to 4. So for this one here, the thought process that I'm going through is if I'm looking for a point of inflection, the first thing I'm thinking of here is that g double prime has to change signs. So g double prime has to change signs. But now we have to think of how many different ways could you think of g double prime. G double prime is also the derivative of g prime. And now in calculus, the derivative tells you the slope of a function. So what we could also look at is the slope of g prime. So what we're really looking for here is when does the slope change signs? And the slope will change signs when the graph switches from decreasing to increasing or from increasing to decreasing. So looking at that over here, Notice at x equals -1 that the graph changes slope. There's a slope change from negative to positive. And if we had to write an explanation here, we could just say we know this happens because the graph changes from it changes from decreasing to increasing at x equals -1. And then the second change is going to occur at x equals 2, where notice at this location, the graph changes from increasing to decreasing. So the slope of g prime changes from positive to negative.